The 27th of May, 1942, dawned with a deceptive calm over the North African desert near Gazala, Libya. British tank crews huddled inside their Crusader tanks, sweat already streaming down faces blackened with oil and sand, when the German panzers appeared on the horizon like steel mirages. Within hours, Rommel's Afrika Korps would shatter the British armored formations, exposing a catastrophic truth that British military planners had desperately tried to ignore. Their tanks were death traps on wheels, mechanically fragile coffins that broke down more often than they fired their guns. Major General Herbert Lumsden watched through binoculars as another Crusader tank ground to a halt, smoke billowing from its engine compartment. No enemy shell had struck it. The cooling system had simply failed, as it had on dozens of other British tanks that morning. This scene would repeat itself across every theater where British armor fought, from the deserts of Libya to the bocage of Normandy, a mechanical nightmare that would cost thousands of British lives and force Churchill's government into an uncomfortable dependence on American industrial might. The story of the Cromwell tank's failure is not merely one of engineering shortcomings, though those were profound. It is a tale of institutional pride colliding with industrial reality of a nation that had ruled the waves for centuries, discovering it could no longer master the land. The Cromwell, Britain's great hope to match German Panthers and American Shermans, emerged from factories in 1943 with specifications that looked impressive on paper. A Rolls-Royce Meteor engine producing 600 horsepower, a top speed of 40 miles per hour, and armor that could theoretically withstand German anti-tank guns. Yet, from the first field trials conducted in the muddy training grounds of Bovington, Dorset, British tank crews knew something was profoundly wrong. The Cromwell's Christie suspension system, borrowed from a 1930s American design, created a ride so violent that gunners could barely aim while moving. The tank's turret ring, designed to accommodate a 75mm gun, was too small to accept the more powerful 17-pounder that could actually penetrate German armor. Most damningly, the Cromwell suffered from chronic mechanical failures that left it stranded far more often than it reached its objectives. According to historical records examined by military historian John Buckley in his 2004 work, British Armor in the Normandy Campaign, British tank regiments reported mechanical failure rates exceeding 30% during the Normandy Campaign, with some units losing more tanks to breakdowns than to enemy action. The Cromwell's gearbox in particular proved catastrophically unreliable, with crews reporting that shifting gears required such force that drivers often needed assistance from other crew members. Meanwhile, across the Atlantic, American factories were producing a tank that would become legendary not for its superiority in combat, but for something far more valuable in modern warfare. It simply refused to quit. The Sherman tank, derided by some historians as inferior to German panzers, possessed a quality that no amount of armor or firepower could replace. It worked, mile after grinding mile, day after punishing day. The first week of June, 1944, found Lieutenant Colonel George Taylor of the American 4th Armored Division conducting an exercise that would have been unthinkable for British tank commanders, a 2,000-mile road march from Camp Boose, Arizona, to Camp Polk, Louisiana. His battalion of 54 Sherman tanks would complete this journey with only 2 mechanical failures, both minor and repaired within hours. This single exercise demonstrated a fundamental difference in design philosophy that separated American and British armor development. The Sherman's reliability stemmed from a deliberate choice by American engineers to prioritize mechanical simplicity over theoretical performance. While British designers at Vauxhall Motors and Leyland Motors pursued complex solutions to squeeze every ounce of performance from their designs, American engineers at Chrysler's Detroit Tank Arsenal embraced a radically different approach. The Sherman used a proven radial aircraft engine, initially the Continental R975, producing 400 horsepower. That was deliberately run below its maximum capacity to ensure longevity. General Jacob Devers, commander of American armored forces in Europe, understood this distinction with painful clarity. In a report dated August 12, 1944, submitted to General Dwight Eisenhower, Devers noted that American armored divisions maintained operational readiness rates of 85 to 90%, while British armored divisions struggled to keep 60% of their tanks operational. The implications for battlefield effectiveness were staggering. An American armored division could sustain operations for weeks. A British armored division needed constant pauses for mechanical repairs. The Cromwell's Meteor engine, though powerful, represented everything wrong with British tank design philosophy. Derived from the legendary Merlin engine that powered Spitfire fighters, the Meteor was over-engineered for tank use. Its aluminum construction made it vulnerable to damage from the constant vibration of tank movement. Its complex cooling system required pure water, nearly impossible to obtain in combat conditions, and its fuel consumption was voracious, limiting the Cromwell's operational range to barely 100 miles. British tankers learned to dread the mechanical inspections that revealed problems American crews rarely encountered. Corporal James Donovan of the 7th Armored Division recorded in his diary, preserved in the Imperial War Museum archives, an entry from July 19, 1944, describing a typical day with Cromwell tanks. Rose at 0500 hours. 3 of our 12 tanks failed to start. By noon, 2 more had thrown tracks. By 1600 hours, only 5 tanks remained operational. We hadn't seen a single German all day, but half our squadron was out of action. This context comes from military maintenance records held at the British National Archives in Kew, which paint a devastating picture of British armor reliability. Documents from the 21st Army Group's mechanical services reveal that during Operation Goodwood, the massive British armored assault of July 18 through 20, 1944, British tank regiments lost more than 200 tanks to mechanical breakdown, compared to fewer than 50 American tanks suffering similar fates during comparable operations. The Sherman's transmission, developed by the Spicer Manufacturing Company, represented another triumph of practical engineering. Its controlled differential steering system allowed drivers to maneuver with precision while placing minimal stress on components. The Cromwell's gearbox, conversely, required such brutal force to operate that drivers frequently damaged gear teeth, leading to complete transmission failures that could take days to repair. The 19th of November 1941 marked the beginning of Operation Crusader, Britain's attempt to relieve Tobruk and drive Rommel's forces from Cyrenaica. For the British armor crews climbing into their Crusader tanks, the Cromwell's predecessor, that morning brought a terrible education in the gap between peacetime testing and combat reality. Within 3 days, British armored brigades had lost more tanks to mechanical failure than to German guns, a pattern that would haunt British armor throughout the war. Brigadier William Carr, commanding the 4th Armored Brigade, watched his tank strength evaporate not from enemy action, but from a cascade of mechanical disasters that began almost immediately after crossing the wire into Libya. Sand filters, supposedly designed to protect engines from the fine North African dust, clogged within hours. Cooling systems, tested in the relatively mild climate of England, boiled over in the 110-degree desert heat. Tracks, adequate for European terrain, stretched and broke under the abrasive punishment of sand and rock. The Germans monitoring British radio traffic were astonished. Oberst Friedrich von Mellenthin, intelligence officer for the Afrika Korps, recorded in his memoir, Panzer Battles, that German intercepts revealed British tank units reporting mechanical casualties at rates that German planners initially dismissed as deception. "We could not believe," von Mellenthin wrote, "that a modern army would field tanks so poorly suited to desert warfare. We assumed the British were attempting to mislead us about their actual strength." Meanwhile, American observers attached to British units were documenting the disaster with clinical precision. Colonel Raymond McLean, sent by the United States War Department to assess British armor tactics, filed a report on January 7, 1942, that landed on General George Marshall's desk like a bombshell. McLean's assessment was brutal. British tanks were fundamentally unsound for sustained operations, suffering from chronic mechanical fragility that renders them unsuitable for the demands of modern mobile warfare. The Crusader tank, which equipped most British armored regiments during Operation Crusader, embodied every flaw that would later plague the Cromwell. Its Liberty engine, a holdover from World War I design, was powerful but catastrophically unreliable. Crews reported that simply starting the engine required elaborate procedures that often took 30 minutes or more. Once running, the engine consumed fuel at such prodigious rates that Crusaders required refueling every 70 miles, assuming they traveled that far without breaking down. British tanker trooper Jake Wardrop of the 3rd Royal Tank Regiment described the ordeal in a letter home dated December 2, 1941, now held in the Little Hart Center for Military Archives. "We spend more time repairing our tanks than fighting. Yesterday we were ordered to advance 15 miles. Only 4 of our 14 tanks completed the journey. The others broke down with various ailments: thrown tracks, failed fuel pumps, seized engines. The Germans don't need to fight us. They merely need to wait for our tanks to destroy themselves." The mechanical failure rates during Operation Crusader reached catastrophic proportions. British maintenance records, declassified in 1972, reveal that by the end of November 1941, British armored brigades reported operational readiness rates below 40%. More than 300 British tanks were listed as casualties, but German records showed they had destroyed fewer than 100. The remainder had simply broken down and been abandoned when their units retreated. This pattern continued through every subsequent North African campaign. During the Battle of Gazala in May and June 1942, British armored divisions began the battle with over 300 tanks, but could field fewer than 100 by the battle's end. German intelligence officers, examining captured British tanks, were puzzled by the frequency of mechanical failures. German tank designs of the period were hardly paragons of reliability, yet they consistently outlasted their British counterparts. The 8th of March 1943 witnessed an event that would reshape Allied armor doctrine. The United States 2nd Armored Division completed a 1,000-mile road march from Fort Benning, Georgia, to the Desert Training Center in California with a mechanical availability rate of 96%. General George Patton, observing the exercise, understood immediately that American armor possessed a decisive advantage that had nothing to do with armor thickness or gun caliber. His tanks could get to the battle and keep fighting. The Sherman's reliability emerged from a design philosophy rooted in American industrial practice. Engineers at the Detroit Arsenal Tank Plant, which began producing Shermans in April 1942, approached tank design with the same principles that made American automobiles dominant. Use proven components, design for ease of maintenance, and prioritize reliability over theoretical maximum performance. This pragmatic approach contrasted sharply with British design philosophy, which pursued technical sophistication often at the expense of battlefield practicality. Major James Burt of the 66th Armored Regiment described the Sherman's mechanical resilience in an after-action report filed September 23, 1944, following the breakout from Normandy. "Our battalion traveled over 400 miles in 17 days, engaging the enemy continuously. We began with 48 tanks and ended with 46 operational. Both casualties were from enemy action. Not a single tank was lost to mechanical failure. Maintenance consisted primarily of track adjustments and oil changes, performed by crews without specialized mechanical training. The Sherman's Continental radial engine, though producing less power than the Cromwell's Meteor, was designed with massive reliability margins. Engineers deliberately ran the engine at 75% of its maximum rated output, ensuring that components experienced minimal stress. The engine's air cooling system, while less efficient than liquid cooling, eliminated the complex radiators and pumps that plagued British tanks. When a Sherman's engine required maintenance, crews could remove and replace it in under 4 hours using standard tools. British tankers who transitioned to Sherman tanks under the Lend-Lease program experienced what felt like a revelation. Lieutenant Peter Beale of the Nottinghamshire Yeomanry recorded his impressions after his regiment converted from Cromwell's to Sherman's in October 1944. "The American tank is a tradesman's tool, rather than a precision instrument. Everything about it suggests it was designed by men who understood that tanks must work, day after day, regardless of conditions. The engine starts reliably, the transmission shifts smoothly, the tracks stay on. These may sound like minimal expectations, but they represent luxuries we never enjoyed in British tanks." The Sherman's transmission system, developed through collaboration between Spicer and Chrysler engineers, incorporated lessons from decades of automotive development. Its synchronized gearbox allowed smooth shifting under load, and its controlled differential provided reliable steering without the violent mechanical shocks that destroyed British gearboxes. British tanker training included instruction on double clutching and other techniques to minimize gearbox damage. Sherman drivers simply shifted gears and moved on. Maintenance data from American armored divisions in Europe, compiled by the Ordnance Department and declassified in 1978, reveals the Sherman's remarkable durability. During the period from June 6 through August 31, 1944, encompassing the Normandy campaign and breakout, American armored divisions reported an average mechanical availability rate of 88%. Component failures, when they occurred, clustered around wear items, tracks, road wheels, and bogie wheels. Engine failures, transmission failures, and gearbox failures, the chronic problems that devastated British tank units, were relatively rare. The economic implications were staggering. Britain, fighting a war that had already bankrupted the empire, could ill afford tanks that required constant expensive repairs and component replacements. Each Cromwell represented months of scarce industrial capacity, and each breakdown meant that investment sat immobile, contributing nothing to victory while consuming precious resources for repairs. The 6th of June, 1944, brought the greatest armored test in military history when Allied forces stormed the Normandy beaches. British tank crews, rolling off landing craft onto French soil, carried with them both the newest Cromwell tanks and the accumulated weight of years of mechanical disappointments. Within weeks, the Normandy hedgerow country would prove the final, decisive testing ground where British and American tank philosophies met the crucible of sustained combat. Operation Goodwood, launched July 18, 1944, represented Britain's attempt to prove their armor could match American battlefield effectiveness. Field Marshal Bernard Montgomery committed 3 entire armored divisions, the Guards, 7th and 11th, to a massive thrust toward Caen, intending to break through German defenses and unleash British armor into the open country beyond. The operation began with over 800 British tanks, the largest armored assault Britain had mounted since the war began. What followed exposed every weakness that had plagued British armor since 1940. Cromwell tanks, advancing across the open ground south of Caen, began breaking down almost immediately. The violent motion of crossing shell-cratered terrain caused gearbox failures. The dust thrown up by hundreds of tanks choked air filters and caused engine overheating. Track pins sheared under the stress of constant maneuvering. By the end of the first day, British armored regiments reported operational readiness rates dropping below 60%. Major General George Roberts, commanding the 11th Armored Division, watched in frustration as his tank strength evaporated. In a message to Corps headquarters transmitted July 19, 1944, and preserved in British official war diaries, Roberts reported, "Have lost 126 tanks to all causes. Estimate 40% mechanical casualties. Request immediate resupply of gearboxes, engine components, and recovery vehicles. Cannot sustain operations at current mechanical loss rate." German defenders, though outnumbered, noticed the British predicament. Hauptmann Hans von Luck, commanding a battle group in the 21st Panzer Division, recorded in his memoir that German troops observed numerous British tanks immobilized with no apparent battle damage. "We realized," von Luck wrote, "that the British tanks were destroying themselves. We could hear them from our positions, the grinding of failing gearboxes, the screaming of engines pushed beyond their limits. We did not need to destroy these tanks, we merely needed to survive until they broke down." Contrast this with American operations during the same period. The United States First Army's armored divisions, fighting through the bocage toward St. Lo, maintained mechanical availability rates consistently above 80%, despite terrain and conditions identical to those facing British forces. The difference was not in crew quality or tactical doctrine. It was in the fundamental reliability of the machines. Technical Sergeant Robert Rowe, a maintenance supervisor with the 3rd Armored Division, described the American experience in a letter dated July 25, 1944. "We perform scheduled maintenance every 75 miles, which takes about 2 hours per tank. Oil changes, track adjustment, inspection of bogies, and road wheels. Between maintenance periods, the tanks just run. We rarely see the catastrophic failures that seem routine with British equipment. Their mechanics work around the clock trying to keep tanks operational. Our mechanics spend most of their time on preventive maintenance." The Sherman's design philosophy proved its worth in the grinding attrition of Normandy fighting. When mechanical problems did occur, they were usually simple to diagnose and repair. The tank's modular design meant that components could be swapped quickly. The British design philosophy of sophisticated integration meant that Cromwell failures often required factory-level repair, effectively writing off the tank for weeks or months. British official histories, particularly Ellis's victory in the West, acknowledge these problems with careful diplomatic language, noting that mechanical reliability proved a persistent challenge for British armored formations. Declassified maintenance records tell a harsher story. By August 1944, some British tank regiments reported operational readiness below 50%, with waiting lists for gearbox replacement stretching weeks into the future. The 23rd of September, 1943, found Winston Churchill in a contentious meeting with his chiefs of staff, confronting a truth that threatened British pride and strategic independence. Reports from North Africa, Sicily, and Italy all told the same story. British tanks were mechanically inferior to American designs, and British industry could not match American production quality or quantity. The Prime Minister faced an unpalatable choice: accept dependence on American armor, or continue sacrificing British tank crews to mechanical failures. The roots of British tank inadequacy ran deeper than mere engineering mistakes. They reflected the fundamental limitations of Britain's industrial base, overstretched by 5 years of war and centuries of underinvestment in manufacturing infrastructure. British tank factories, many converted from locomotive works or automotive plants, lacked the precision tooling and quality control systems that American mass production had perfected during decades of civilian manufacturing. Documents from the Ministry of Supply, declassified in 1995, reveal the scope of Britain's production problems. Quality control reports from Leyland Motors' tank production facility in Lancashire showed rejection rates for gearbox assemblies exceeding 20% during 1943. Vauxhall Motors, producing tank engines at Luton, reported similar problems with cylinder head castings and crankshaft forgings. The precision required for reliable mechanical systems exceeded what British wartime manufacturing could consistently deliver. Lord Beaverbrook, Minister of Aircraft Production and former Minister of Supply, wrote candidly to Churchill on November 8, 1943, in a letter preserved in the Churchill archives. "We must face facts. American manufacturing capacity exceeds ours by an order of magnitude, and their quality control systems produce components to tolerances we cannot match with current facilities. Our tank designs may be theoretically sound, but our ability to manufacture them reliably is inadequate. We are sending our men into battle with equipment that fails not because the design is flawed, but because our manufacturing cannot execute the design properly." The Cromwell tank exemplified this crisis. Its Rolls-Royce Meteor engine, descended from the legendary Merlin, should have been superb. But the Merlin was manufactured to aircraft standards, with tolerances measured in thousandths of an inch, and quality control that rejected components American automotive plants would have considered acceptable. Adapting the Meteor for tank use required maintaining aircraft-level precision in facilities equipped for much cruder automotive work. The result was engines that performed magnificently when properly manufactured, but failed catastrophically when tolerances slipped. British tank crews paid the price for these industrial limitations. The 2nd Fife and Forfar Yeomanry lost more tanks to mechanical breakdown during the advance across France in August and September 1944 than to German action. Their war diary, held at the National Archives, records a litany of mechanical disasters. 8th of August, 3 tanks broke down during approach march. 12th of August, gearbox failure immobilized 2 tanks during engagement with enemy. 17th of August, 5 tanks require engine replacement. 22nd of August, unit operational strength reduced to 14 tanks from establishment of 48, primarily due to mechanical casualties. The American Sherman production system, by contrast, benefited from decades of automotive mass production experience. The Detroit Arsenal tank plant, when it began Sherman production in April 1942, applied assembly line techniques perfected by Ford, General Motors, and Chrysler. Workers used standardized tools, components were manufactured to consistent specifications, and quality control caught defects before assembly. The result was tanks that, while perhaps less sophisticated than British designs on paper, actually worked when delivered to combat units. Statistical analysis from the period reveals the full extent of the disparity. Research by military historian Rob Griffin, published in his 2008 work, Allied Armored Fighting Vehicles, found that Sherman tanks in European operations averaged over 300 hours of operation between major mechanical failures, requiring more than 12 hours to repair. Cromwell tanks averaged less than 100 hours between similar failures, and catastrophic failures requiring factory-level repair occurred 3 times more frequently. The 14th of January, 1945, marked the beginning of an exercise that would become legendary in American armored circles. The 6th Armored Division, preparing for final operations against Germany, conducted a road march from Camp Cook, California, to Fort Knox, Kentucky, a distance of 2,047 miles across the varied terrain and climates of the American West and Midwest. 54 Sherman tanks began the journey. 53 completed it without significant mechanical problems. The single failure was a thrown track quickly repaired by the crew. This achievement, documented in the 6th Armored Division's official records, held at the National Archives in College Park, Maryland, represented more than just mechanical reliability. It demonstrated that American armor possessed strategic mobility that British tanks could never match. An American armored division could be transported thousands of miles and arrive ready to fight. A British armored division required extensive mechanical rehabilitation after any significant movement. Colonel Frederick Brown, commanding Combat Command Alpha of the 6th Armored Division, filed a detailed report on February 11, 1945, analyzing the march's success. His conclusions centered on the Sherman's fundamental design soundness. The tank's mechanical systems are designed with sufficient margin that normal operational stresses do not approach failure thresholds. The engine operates well below maximum capacity. The transmission tolerates the constant load changes of road marching. The suspension absorbs road shock without damage. Most significantly, the tank systems are designed so that crews can perform all routine maintenance with standard tools and minimal training. British tank units could not dream of similar achievements. The logistics of moving a British armored division by road required mobile workshops, extensive spare parts inventories, and plans for recovering tanks that would inevitably break down. A 1944 study by the British War Office, examining the feasibility of rapid redeployment of armored divisions, concluded that mechanical reliability concerns made road movement of more than 200 miles impractical for British tank units without substantial recovery and repair assets accompanying them. The Sherman's track system illustrated American design pragmatism. Each Sherman track consisted of 79 steel links, each weighing roughly 25 pounds, and designed to be replaced individually by tank crews. Track pins were sized so that standard sledgehammers could drive them in or out. British tank tracks, by contrast, often required special tools and techniques for repair, meaning that a thrown track could immobilize a British tank for hours or days, while a Sherman crew could replace damaged track sections in under an hour. Lieutenant Edward Walsh of the 4th Armored Division recorded a telling incident in his diary entry for December 19, 1944, during the Battle of the Bulge. Through a track while maneuvering to engage German armor. Crew had track repaired in 47 minutes while under sporadic artillery fire. Continued mission without requiring assistance from maintenance units. Later observed a British Cromwell with track damage. The crew could not repair it themselves and was awaiting recovery vehicle. Fuel efficiency, often overlooked in discussions of tank reliability, represented another American advantage. The Sherman's radial engine, running conservatively, achieved operational ranges of 120 to 150 miles on flat terrain. The Cromwell, with its powerful but thirsty Meteor engine, struggled to exceed 90 miles per tank of fuel. In mobile operations, this difference was decisive. American armored spearheads could sustain advances that would have left British tanks stranded awaiting refueling. The cumulative effect of these reliability advantages reshaped Allied strategic planning. General Eisenhower increasingly relied on American armored divisions for rapid exploitation operations, while British armored units were assigned to more positional roles. This was not a reflection on British tactical skill or crew courage, but a pragmatic acknowledgement that American tanks could sustain the pace of mobile operations, while British tanks could not. The Battle of the Bulge, from December 16, 1944, through January 25, 1945, provided final proof. The Third Army's 4 armored divisions drove over 100 miles through winter conditions to relieve Bastogne, maintaining operational tempos that would have been impossible with British armor. Patton's tanks arrived ready to fight, not strung out along roads awaiting recovery vehicles to collect mechanical casualties. The 8th of May 1945 brought victory in Europe, and with it an accounting that British military planners could no longer avoid. 5 years of armored warfare had rendered an unambiguous verdict. British tank design philosophy had failed. The Cromwell tank, Britain's most advanced production tank of the war, had proven mechanically inferior to the American Sherman in every measurable way. The numbers told a story that pride could not obscure. British post-war analysis, particularly the report of the Tank Board convened in July 1945, conducted a searching examination of why British armor had underperformed. The report's conclusions, finally declassified in 1988, were devastating. British tanks suffered mechanical failure rates 3 times higher than American equivalents. British tank production costs exceeded American costs by 40%, while delivering inferior reliability. British tank designs required twice as many man-hours for maintenance per operating hour as American designs. Major General Raymond Briggs, who served on the Tank Board, wrote in his personal memoir that the investigation revealed systemic failures of engineering philosophy, manufacturing quality, and procurement priorities that left the British Army equipped with armor that was simply not fit for purpose. The Cromwell's failures were not aberrations, but the predictable result of design choices that prioritized theoretical performance over practical reliability. The human cost of these failures could never be fully quantified. How many British tankers died when their tanks broke down during enemy contact, leaving them stranded and vulnerable? How many tactical opportunities were lost because British armored units could not sustain operations due to mechanical problems? How many battles might have ended differently if British armor had possessed Sherman-level reliability? Trooper Stanley Christopherson of the 4th County of London Yeomanry, later Lord Christopherson, reflected in his memoir, An Englishman at War, on the frustration of serving in mechanically unreliable tanks. We knew the American chaps in their Shermans could depend on their tanks. They could plan operations knowing their tanks would be there when needed. We planned operations hoping our tanks would still be running. That difference in confidence affects everything: tactics, morale, effectiveness. A tank that works is worth infinitely more than a tank that's theoretically superior, but perpetually broken. The Sherman's 2,000-mile endurance became a benchmark that post-war British tank design finally attempted to meet. The Centurion tank, entering service in 1945 too late for wartime use, reflected hard lessons learned. It prioritized mechanical reliability, used proven components, designed for ease of maintenance, and tested extensively under field conditions before full production. The Centurion became one of the most successful tank designs of the Cold War era precisely because it abandoned the philosophy that had doomed the Cromwell. American armor had won not through superior firepower or thicker armor, but through the unglamorous virtue of reliability. The Sherman tank could be outgunned by German Tigers and Panthers, but it got to the battlefield, fought, took damage, returned for repairs, and fought again. British tanks too often never made it to the battlefield, or broke down during action, or required such extensive repair that they spent more time in workshops than in combat. The final irony was that British dependence on American armor continued long after the war ended. Britain's chronic industrial weaknesses, exposed by wartime demands, could not be quickly remedied. British armored units continued using Sherman tanks and their derivatives through the 1950s, a quiet admission that British industry could not yet produce armor reliable enough for modern warfare. The Cromwell tank's failure and the Sherman tank's success reflected deeper truths about industrial warfare in the 20th century. Victory required not just brave soldiers and sound tactics, but also industrial systems capable of producing reliable, maintainable equipment in enormous quantities. Britain, for all its military traditions and engineering brilliance, could not match American mass production capability. The Cromwell's mechanical failures were symptoms of this larger industrial reality. On November 11, 1945, the British Army conducted a victory parade through London. Sherman's dominated the armored contingent, not Cromwell's. The message was clear to anyone who understood. British armor had survived the war, but American engineering had won it. The Cromwell tank remained a symbol of British ambition, but the Sherman tank represented the hard reality of what actually worked when lives and victory